Welcome to This Explainer. Today, we're demystifying exactly how electrical circuits work, specifically breaking down the fundamental differences between open and closed systems. Whether you're dealing with a simple everyday flashlight or the insanely complex wiring hiding right there inside your walls, understanding these two basic states is absolutely crucial. It's your ultimate key to grasping how electricity actually functions. Here is our quick agenda for today. First, we'll cover the basics of electric circuits. Second, the open circuit state. Third, the closed circuit state. And finally, we'll compare the circuit states head-to-head. Section 1. Basics of electric circuits, the foundation of electron flow. So at its core, what actually is an electric circuit? Well, it's simply a closed-loop network. It's basically a dedicated path, usually built with electrical wires, that connects a specific network of components. And the entire purpose of this structural loop is to create a perfect environment where electrons, those tiny charged particles that make up electricity, can easily flow. Without this specific path, electricity literally has nowhere to go. It relies entirely on this continuous highway to do its job. Think of this as the physical journey of the electron. It happens in 3 basic steps. Step 1, they always begin at the active energy point, which we call the source. That's usually something like the positive end of a battery. Step 2, they travel along that conductive wire, doing all the hard work along the way, whether that means powering a motor, generating some heat, or lighting up a bulb. And then step 3, they ultimately arrive back at the end point, which is known as the return or the negative end. It's essentially a continuous round-trip ticket. Now, here's the real catch. For this circuit to actually be complete and functional, there must be at least one continuous, unbroken loop stretching from that positive source all the way back to the negative return. If that loop is compromised in any way whatsoever, well, the journey stops entirely. The electrons halt in their tracks, and the power just vanishes. It literally only works when the loop is whole. Section 2. The open circuit state. The broken path. So what happens when things break down? The absolute golden rule of an open circuit is this. There is no electrical connection occurring between the power source and the load. And by load, I just mean whatever device you're trying to power up. Because the path is incomplete, the electric current absolutely cannot flow from the active energy source to your connected components. The bridge is, quite simply, out. To picture this in a real-world scenario, just imagine a simple DC battery hooked up to a standard light bulb. When the switch is left open, that physical bridge is broken. The electric current simply cannot jump across that physical gap from the battery to the bulb. And the result? The bulb remains completely unlit. The energy is there, but it has absolutely nowhere to travel. Because that path is fundamentally broken, the entire circuit is operating in an off condition, meaning it just does not conduct electricity. As a direct result, zero potential difference occurs between the 2 terminals of that open switch. It's essentially a dead end for the energy. Without a connected path, there's absolutely no electrical pressure pushing those electrons forward. And it's really important to realize that a manually open switch isn't the only thing that causes this state. If components naturally disconnect or break down over time, boom, the circuit immediately functions as an open circuit. This usually shows up as a fault condition in your everyday devices. Interestingly enough, if you accidentally use insulating devices instead of true conductors in your setup, electricity won't flow either. So you end up creating an open circuit even if the physical path looks perfectly connected to the naked eye. Section 3. The closed circuit state. The complete path. Now, let's flip the script entirely. In a closed circuit, everything is working exactly as intended. The path is completely intact, forming a perfect, unbroken closed loop. And this is the magic state because it allows the electric current to flow freely, continuously, and efficiently right from your active energy source straight to the connected load or any other components you have in your system. But for this continuous flow to actually happen, we require 2 essential things working together in perfect tandem. First up, we need conducting materials. Think of a copper wire forming a solid physical bridge. Second, we need an active element. This is your battery or maybe a PV cell, which is just a photovoltaic solar cell, acting as the voltage source to actively push that current right through the closed loop. Which brings us to the everyday reality of how we control all this. The mechanical switch. The switch acts as the ultimate gatekeeper of the entire process.
We use it to actively make the circuit, shifting it into the on position to create that seamless closed loop. Or, on the flip side, we use it to break the circuit, shifting it into the off position to purposefully create an open loop and stop the flow of electrons dead in their tracks.
Section 4. Comparing circuit states. The head-to-head showdown. Even symbolically on electrical diagrams, these two states are highly distinct. It's kind of like a secret visual language that engineers use. An open circuit is represented by empty parentheses, brilliantly showing that exact physical gap in the path. Meanwhile, a closed circuit features a dot perfectly centered right in the middle of those parentheses, representing a solid, complete, and fully active connection. When we step back and look at the actual movement of current, the contrast is super stark. In an open electrical circuit, it's a total blockade. The current simply does not flow anywhere. It is completely stagnant. But in a closed electric circuit, the current actively and dynamically flows from the positive charge, transferring active energy straight from the source directly to the load to do all the heavy lifting. And this physical blockade directly impacts potential difference too. In an open circuit, the potential difference simply does not occur between the two terminals. The pressure is just gone. But switch that path closed, and suddenly the potential difference very much occurs, acting as the driving, invisible force that powers the whole shebang. If you were to synthesize all of this into a quick cheat sheet, it clearly contrasts the incomplete, non-conducting off state of the open circuit with the complete, conducting, continuously on state of the closed circuit. It really all boils down to one simple thing: whether that active energy has an unbroken path to travel. These are the absolute fundamental rules of electricity. So the very next time you flip a light switch in your house, I want you to ask yourself a quick question. Did you just build a continuous copper bridge for electrons to flow? Or did you just break one? It's a pretty powerful way to look at the invisible infrastructure all around us. Because if opening and closing a simple loop can power our world, just imagine what happens when we start adding millions of complex pathways to the mix. Thank you so much for joining me for this explainer, and remember to keep questioning exactly how the world works.